Hey folks, Dr. G here, and welcome to your Friday asynchronous class. So I really like these simulation things here, and I thought it'd be nice to just sort of put together a video of me going through some of these things, and so that you sort of have a guide as you're doing it. So it'd be sort of like we're working through this together here. Okay, so for the homework. Let's see, I told you have to do section 1.1, 1.2a, 1.2b, and all of section 3. So this stuff right here. And that comes from this. So first I clicked on that link, and then this comes up. Actually, no, let's start fresh. So I click on this link. We get, there we go, it popped up. And then if I click on this for the browser compatible version, it shows up, and now we can interact with this thing in a moment. So while that's loading, there we go. Okay, so here's our energy levels. We can click on them. We know this from class already. Let's see. Okay, I'm here now. We'll start with the square well. Okay, the energy levels are thin green lines, and the energy level you're currently in is highlighted in red. So right now we're in psi 1. This is the ground state. This is the lowest energy state. Is there? I can click on that, click on the one up. Now we're there, etc. Okay. And of course, the thing being shown here is the probability density function. Right? There's a probability density function. There's the wave function. So let's leave it in probability density because that's where the exercise started. And now let's see here. Okay, if we click the double arrow symbol on the bottom of the well and drag it up and down, what's going on with that? So we talked about this a little bit in class 2, but just for the sake of completeness, we'll start at the beginning, right? So if I drag this thing up and down, you note that, the values of the energy levels are shifting, right? So here the ground state is at 1.20, and if I shift this thing down, now it's at, let's see, where is it? There we go. I've got it down to exactly 0. So if I drag this thing around, it does change the values of the energy levels. But you'll note that relative to each other, they don't change. And so this is sort of, I talk about establishing a frame of reference, and that energies they're all relative. So, if someone says this is the absolute energy of something, they're still referring to standard conditions, right? Somebody had to make that up. Okay, what temperature is standard? What pressure, whatever the case may be. So these things energies are always compared to something. So that's what we're seeing here is if I slide this thing up and down, all these energy levels are still the same distance from each other. So relative to each other, these energy gaps, these differences in energies are the same. So we're just kind of shifting everything up all together, up and down. All right, so that's what's going on in 1.1a. Now 1.1b, if we click on the double arrow at the right side in the middle of the well and drag it left and right, explain what's going on there. Okay, so I click on the double arrow symbol at the right hand side. That's this one. And if I drag that left and right, you see what's going on here. Okay, so this is super cool. So you notice that all these energetic states and they get pretty cool looking too when they get bigger, right? So if I click one of these, now we got that. Let's see what the wave function looks like. Ooh, cool, right? Go back to probability density function. And by the way, the wave function, it has a real and an imaginary part. Right? And so when we do that thing where I would talk about squaring wave functions, you're multiplying the wave function by its complex conjugate. So basically, if there's an I in front of something, it becomes a negative I in its complex conjugate. Yeah, cool. So let's go back to probability density. So, if we were trying to figure out, if we were going to make a measurement of where the particle is here, this is what our probability density function looks like for this particular thing here. So we see that there's places where we're likely to find it and places where we're highly unlikely to find it. In fact, when it touches 0, you will never see the particle there. So, this is an interesting difference between a quantum and classical system in that, if you had, say you had a tube with a marble in it, and you shook that tube up and you look where the marble is, and it's a classical system, it's large, It's longer length scales, heavier masses, hotter temperatures, right? So if I shake that up and I look where the marble is, if there's two different places that I saw it, we know that between those observations, that marble had to be kind of everywhere in between there at some point, right? It couldn't have skipped part of it. But when you measure a quantum particle in a box like this, it could be in this probability density right here, in this area, or it could be here, but it'll never have been there. So you can measure a bunch of times and you won't see it show up in between. Okay, well, we're getting off track here. So the point is we're trying to look at what happens when I make the box bigger or smaller, right? That's what's going on. The size of our box here, we're making, this is our width parameter. So if I make it big, the box is wider. So we're giving the particle more space that we're allowing it to bounce around in. So if I make this thing a lot bigger, we see that there's a lot more energy levels. There's more possible energy levels. Whereas if I bring it in really close, there's very few. Here we only have a ground state, a first excited state, and a second excited state. That's it. There's just 3 energy levels here. That's all we can do. If we're able to trap a particle in a box that's small. But if we trap it in a bigger box, now there's a lot more different energy levels it could be. Okay, so part B of 1.1 says click on the double arrow symbol at the right-hand side in the middle of the well and drag it left and right and explain the behavior of the energy levels. What's going on with that? Okay, so that's this thing right here, this width parameter. I can change the width of the particle in a box. This is the width of the box where the particle is trapped. And we see that if we bring it really wide, we see a lot more energy levels. Right? The value of the energy level doesn't get any higher, right? So like if this is 10 right here, we can change the height of the box, right? If we make the box exactly 10, that's the, so this highest energy level is 9.82, right? So that's just not quite high enough to escape out of the box, at least in a classical sense. It's not talking about tunneling here. That's a quantum effect, right? But basically, this is the highest energy level that we can calculate for our particle in a box. It's less than 10, basically. So these are the states that are bound states where the particle is trapped in the box. And basically, the smaller we make the width, the smaller the particle, the smaller the box is, the fewer energy states we have. Right, so it's not like making it bigger makes them get higher energy. Fine, we get a little bit closer to the 10, but really you just get more states. And remember how I always talk about in class where as length scales get longer, the quantum effects start to average out. They get basically, if you describe things in a classical sense, your descriptions get better and better the larger things are. And this is really nicely illustrated by this, right? We have these as the width gets really small, if you look at the difference between like the ground state and the next state up, we're at 1.04, then it jumps all the way to 4.86, right? So these magnitudes that's a considerable amount, right? This is almost a factor of 5, going from the lowest energy to the second lowest energy. But if I make this box really big, now the very lowest energy is minus 0.29. Then we go up to minus 0.26. So now we're in the 1000th place now. So the difference between these energies of these energy levels, we're in the 1000th place. So you can imagine that if, when we say that energy is quantized, we're saying that it has to have certain values and it can't be something in between. So the bigger the box gets, basically, the difference between these energy levels gets smaller and smaller. So this box gets really big. Eventually, you'll get to the point where changing the energy, if we approximate that as being continuous, where we say like, okay, maybe I can have any energy between two given values. That starts to become more and more correct, basically, the larger the box gets, right? Really small box, this is very much a discrete thing, right? Going from, say like 3 to 9, right? That's like a factor of 3 right there. We're seeing much bigger jumps in energy. So the fact that energy is discretized or quantized, it's really pronounced for small things. Make this really big. Now we've got these changes aren't that different, right? So it's still it's still quantized, but it's closer to continuous, right? If I had to say which one of these is closer to continuous, this is certainly, particularly in the lower energy levels, this is much closer to continuous than that is, right? So that's what's going on when we change the size of the box. Basically, we get more energy levels, and they're not higher in energy, but there's more of them, and they're close together. Which, as we say, if we keep getting larger, it gets kind of more classical almost. Okay, part C. Click on the double arrow symbol at the right-hand side of the top well and drag it up and down. Okay, I've played around with this a little bit already, but let's do it again. So if we bring this up and down, okay, this adds more energy levels as well, but it adds more energy levels by making higher energy states, right? So basically, if we increase this thing, there's more, the box is stronger, right? We have this box, how strong is, so we're talking about a one-dimensional box here, right? So, kind of think of more of it like as a pipe that's like infinitesimally skinny. So a particle can only move along one dimension, right? Left to right, that's all it can do. And the ends of the pipe, well, how strong are the ends of the pipe? We have to be, we're scientists. We try to be careful about describing things, right? Well, how strong are they? Well, we have to pick a value. And that's what this is. This is how strong the ends of the pipe are. So interestingly enough, too, let's see, look at where, here, let me pick a value. Here we go. So I chose a height here where there's an energetic state. There's a quantum state here that is just a little bit smaller than the height. So the height is 9.6, and this state is 9.22. So if I'm in that state, the box ends here, right? This vertical pink line, and it ends here. And if you look at the probability density function of where we can find the particle, look what it does out here, right? The box ended here, but somehow you can find the particle outside of the box. And this is quantum weirdness or whatever, right? This is tunneling. Basically, you can, this energetic state, if you look at the value of this energy, it's less than the barrier, right? The barrier, like I said, was like, what was it, 9.6? And the actual energy of the state is 9.22. So, in a classical system, you'd say this doesn't have enough energy to get out. Therefore, it's contained in there completely. But a quantum state, there's actually a probability that, if you measure the position of this particle, you're going to find it in the wall. It's going to be in the barrier. That we're blocking the ends of the pipe with walls, right? And you can find, there's a chance that you'll find the particle in the wall. And this is tunneling. So this is, I mentioned Moore's law, how semiconductors, right, we've been able to pack more and more of those things inside of a microchip over the years in a very predictable way. It's been exponential growth, but that's gonna run out of steam very soon. In fact, it may have already started slowing down a little bit, and part of that is that when these things start getting really small, really short distances, now the idea of confining an electrical current to being on or off, that's a little bit harder to do, because if you try and put a barrier, there's still some probability the electron's on the other side via tunneling. And that's what we're seeing here. If we have a particle that's trapped in this box, there's actually a decent chance we'll find it outside the box, even though it has less than the amount of energy to escape, right? So this is kind of like, if you were at the bottom of a roller coaster and you wanted to, let's see, and you did not have enough kinetic energy to make it over the hill, and yet somehow you found the roller coaster past the hill. It'd be something like that, right? But obviously it's very small, it's a quantum effect. But it's sort of like that, right? If you don't have enough energy to escape, and yet somehow you can still be found outside of the barrier just because of sort of the delocalization of particles. So that's what's going on there, is basically tunneling. So that's pretty cool. All right, that's 1.1b. Let's look at C now. If I click on the double arrow symbol at the right-hand side, drag that up and down. Wait, is that what we just did? Oh, yeah, we did that. Yeah, so this thing, this height, again, that's just, that's making our box stronger. The higher we lift it, and it makes the box weaker, the lower we drop it. And in fact, if you watch the probability density function here, you see it expanding a little bit. the lower I put this thing, right? But if I start making it really big, eventually, the differences are much less pronounced up here, right? Than they are down here, right? So cool. All right, let's see what else we got. Alrighty, on the right-hand side of the simulation, there is a sliding bar where you can vary the mass. I didn't even notice that. Let's see. We can change the mass of this thing. Here it is. Oh, that's cool. So this is something that the definition of the particle in your box, the particle in a box in your book, I think they left the mass out in their description. So this is a more detailed picture. This is good. Yeah, if you look at the mass right here, we're changing it. And let's see what the question says. Explain the behavior. Okay. So let's see. If mass goes down, these energy states are. Let's see here. So let's look at one state. So 4 energy state. So this is the fourth energy level here. There's 1, 2, 3, 4. With the fourth one. And if I make the mass go up, that fourth one drops. The energy of it drops. And if I lower the if I lower the mass, the energy goes up. If I decrease if I increase the mass, it drops. So that's what's going on with the mass here. Alrighty, let's look at 1.1D now. So we're here. On the right-hand side of the sim, there's a sliding bar where you can vary the mass of the particle in the well. Explain the behavior of the energy levels when you do this in your own words and with an equation. All right. Well, let's see. Okay, so here is a little slider here where you can change the mass. So let's just choose one of these energy levels. Let's go with I don't know, let's go with the fourth one. So here's the fourth energy level. If I slide this all the way low as it goes, the energy is up here. It's at 1.56. If I slide it all the way to the right, now it's down to 0.58. So it drops. We have an inverse relationship between the mass and the energy. So the more I raise the mass of the particle, the more the energy level value drops. So basically we see, and if you watch all the lines, they're all, as I lower this, they all kind of go up. If I raise it, they all drop down. Yeah. And the fact that they keep dropping down means that we get more of them too, the larger this thing gets. So, relating this to what I was saying before, as you make the box bigger, things get closer to continuous, closer to classical. So, as the box got bigger, that happened. And also, as we increase the mass, we get more and more states. So sort of our density of states down here gets higher. And basically, here we go. Let's go real big with a real heavy particle. See, now look down here. I mean, these numbers are barely changing from one to the next, right? These energy levels are getting very close together. So if I got a heavy particle in a big box, this thing is getting less and less kind of quantum, right? There's these particularly these lower energy levels. Like, yes, it is still quantum. Everything is quantum. These energy levels do have a discrete, differences in values, but the values are getting closer together. So they're, if you approximated this as continuous, you'd start getting a lot more accurate approximations, right? So we're kind of seeing a similar thing, right? As the particle gets heavier, things are getting more closer to classical. With the density of our states here is getting higher. They're more packed in. There's a higher density of excited states here. So if we look at the textbook here, we've got this expression right here for the particle in the box. This is the value of the energy levels. We see that mass is on the bottom, and it's not mass squared or anything like that. It's just mass. So 1 over mass. So if this thing looks inversely proportional, you'd be correct. It is inversely proportional. But I also want you to understand that as this particle gets heavier, our density of excited states here is getting higher. So things are getting kind of more closer to classical. Okay, let's look at part E now. Push the reset all button. Okay, check. Reset all settings, yes. Okay, we're back to how it started. Now what? Make sure that the bottom panel of the sim displays the probability density. Okay, we have that. All right, we've seen this before. We've got probability density. We hit the play button. It is playing. See, time is going by. This is in femtoseconds. Nothing's happening, right? It's a probability density function. Nothing's happening. All righty. Let's see. You can speed it up to fast. Nothing's happening. Nothing's happening, right? We can try speeding it up, I guess. Still nothing, right? So what happens? Okay, why? Let's see. Do you see this one? All right, and they want us to check different excited states. So let's put this thing up fast so that if it's changing, we're going to see it. And if we click on these different states, is it changing? Now, these probability densities functions are not changing. What if I look at the wave function? Ooh, they're going fast now, right? Yeah, so the wave function is changing. The probability density function is not. So, think about what you need to do to a wave function. Think about what you need to do to a wave function to make it a probability density function. And basically, if you've got, let's slow this thing back down again so we don't get dizzy. So these things, if you multiply them together, think of the functions you're going to get. And in fact, if we choose a time point here where, let's see, let me right there. Hang on. That's pretty close. So right here you see that basically, the, what do we have? The imaginary part here is kind of at its, peak amplitude. And amplitude is just how big the wave is, right? Like if so the waves in the ocean are really tall, one day like a high amplitude day, right? I'm sure everyone says that. So if we stop it at a point where this is really high amplitude, this one's almost nothing. If you squared that, you can see how it would look like that, right? Right. This value is going to become positive. This value is going to stay positive, but get bigger. This one's stay positive, get bigger, right? So here it goes up, down, up, and now it goes up, 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 right? So you can kind of see how the negative values are getting squared, right? So think about what happens if you square these things, right? And again, look at look up what it is to multiply a wave function by its complex conjugate, and then you'll see what's going on with the real and imaginary parts here. Another way to think about it is if this wasn't changing at all and you squared it, it would look the same way, right? But in reality, these things do change, but because there's a real and an imaginary part, when you square them, it's going to stay consistent. Okay, now part F. Push the reset all again. All right. Done. Now what? And then pause and rewind to set the time to t equals 0. Okay. Okay, I already did that. So we're at time t equals 0. Great. Now what? Click the radio button for wave function. Radio button. I guess these things are called radio buttons. Okay, now let's change to wave function. Now what? So we click the button so it says wave function. Great. And check only the real part. Okay, so we only want to see the real part. We already have that. Great. Now what? And let's see. Set the sim speed to 1 level above normal. Okay. I guess that's 1 level above normal. Now we're going to watch that. Okay, cool. So we're seeing this thing flap up and down. Hey, remember that demonstration from class where there's the two guys shaking that jump rope looking thing, right? It looked like this. It's the same kind of deal. All right. We observe. You know from class that psi star psi must be equal to 1 for physically meaningful particle. All right, so what does this mean? If you integrate something and you get 1 underneath, what is it with that function? What is that function? What have you done to it? It starts with an n. N is in nobody, right? And so if you integrate this thing from all space, negative infinity to positive infinity, you get a 1. And basically, this is going from a wave function to a probability density function. you multiply that wave function by its complex conjugate. So it's very much like squaring something, except if there's an I there, like the square root of -1i, if there's an I there, that gets a negative sign in the complex conjugate. So basically, set all the i's to negative i's for this one, and then multiply it by the other one. And then this is going to give you a probability density function. And if you integrate that thing, you're going to get 1, assuming that your psi functions are properly set up to do that, which again, that's a word that starts with n. I'll leave that for you to figure out what I'm talking about. All right, is this the case for all times for what is displayed? Wait, let's see here. Is this the case for all times for what is displayed? Oh, I see. Wait. Oh, I see. So what they're saying is, if you square this thing and take the integral of it, are you going to get 1 every time? So, if it's here and we square that, take the integral, you're going to get some value. If it's at this time and you square that and take the integral, you're going to get a value. Is that value going to be the same all the time, or is it going to change? Basically, the area under the curve, is it changing or staying the same as you watch this thing go up and down? All right, so hopefully you figure that part out. Okay, okay, now check the imaginary box and repeat that part. Okay, so if I check these both and then we let this play, okay, cool. So now they're asking sort of the same thing and say, all right, now if we consider the wave function as the sum of these two things, right? And basically the real part is orange, so that does not have an I in front of it, and the imaginary part is blue, and so that one does, right? So it could be, maybe the orange is a cosine and the blue is a sine, and so it'd be like, cosine of x plus sine of x, something like, cosine of x plus I sine of x, something like that, right? And if you multiply these two together, in that case, now is this quality that the integral of this thing squared is going to be 1? Is that going to hold constant? So the first time, if you square that thing and take the integral under it by itself, is that thing constant? That doesn't look constant to me. But this part, now, basically, you can see how maybe in this case, squaring both of these things and taking the integral, the one can kind of make up for the other one, right? If you've got, here, let me pause it there. Hang on, one more try. One more. There we go. If I pause it there, you see that the area under this thing is big, and this one's almost nothing, right? And then if we go here, it's kind of the opposite, right? The area under the other one. There we go, right? So you can see how basically one can make up for the other one. When the other one is nearly flat, the other one's at its peak. So think about that now, and why do we need this complex conjugate piece, right? So that we have something that's waving, but when we square it, we get a consistent probability density function. So that's kind of what's going on here. We're getting an explanation for why we need the real and complex part of the wave function. That basically, if we only had the one part, and I square that thing, it's going to keep changing on me, right? That's a pretty big value, and that is almost nothing, right? Whereas if I bring the imaginary part back, okay, when this one's almost nothing, now this one's at its peak almost, right? So basically, they kind of make up for each other. So it allows our wave functions to be waving, right? But still, if we square them, and then they'll produce a consistent probability density function is what's going on here. So that's kind of what we're getting from this step. So this is a very important question because it kind of explains why the mathematics needs to include the complex conjugate, right? This psi star psi here, right? Why can't we just have psi squared? This is why. It's because if this thing is, if our wave functions are waving, then there must be two components because basically when we square these things, we have to get a consistent probability density function. And again, when we have that, I hit play, nothing happens, right? Nothing happens here. But if we turn the wave function on, it's moving, right? These things are waving. The wave functions are waving. But because there's these two components and one can make up for the other one, you're going to see that this is sort of what allows the mathematics to work out for us here. Okay, so that's good for F. Let's move on. Okay, so next I said to do part 1.2a and 1.2b. So let's look at that. Wait, 1.2a. Here it is. Here's 1.2, here's A. Alrighty, so, whoops. Drag the up and down symbol in the bottom until it's at -5 electron volts. All right, so down there. There we go. We're at -5 eV. Check. Then set the potential energy value outside to 0. Okay, so we want this thing to be 0. Wait, 0? Oh, there it is. 0. Oh, I see. It tells us the height, but we have that at 0. I believe that's what they want. Let's see. Set the potential energy value outside the box to 0. Yeah, this is right. Okay. Yeah, this will display 5 eV. Correct. Okay. So now we want to drag the width controller in the right to adjust the width of the potential. Okay, so if we adjust the width here, all right, we've done this sort of thing before. Okay, now looking at part A, so we're here now. Vary the width D in steps of 1 nanometer to 2 nanometers. Oh, I see. Okay. Okay, I don't know what width they want us to start at. Let's see. In steps of 0.1 nanometer up to 2 nanometers. So I guess we go as small as we can. Yeah. Okay, so we want to go as small as we can and go in steps of 0.1 nanometer and stop when we get to 2 nanometers. Okay, so we get as small as we can. This is 0.1. And they want us to go in steps of 0.1. Okay, so here's our minimum one. We see that at this height and width, there's actually only one state, the ground state. So basically, if this electron gets excited into a higher energy level, it gets out of the box, right? That's what we're getting at here, that there's only one state here. So if we increase this by 1, by 0.1 nanometers, which we just did here, the value, it drops. So here we have -0.122. Now it goes -2.54. There we go. So they want us to keep doing this and use either Google Sheets or Microsoft Excel, whatever you like to use to make spreadsheets. And you're going to keep recording these numbers. So you're going to keep increasing this in increments of 0.1 till you get all the way up to a width of 2. So there's 2. So when you get to this line, you're good. So this is the largest one we're going to look at. Here's the smallest one we're going to look at, right? So every step of the way, you're going to want to record. What do they tell you to record? Plot the number of bound states. Okay, so as we've mentioned, a bound state, that's an energetic state where the particle is still stuck in the box, right? It's bound in the box. So we started here. There's only one. Here, there's one state again. So you'll end up recording 1 twice, right? So at 0.1, it's 1. At 0.2, it's still 1. At 0.3, it's 2, right? Now we have our excited state that's right here. Well, look at that excited state, right? Look how far outside the box the electron can tunnel. So if it's in this excited state, it has less energy than the strength of the box, right? The amount of energy in the system is less than the strength of the barrier keeping it in, but yet we can still find the particle outside of the box, right? This is quantum tunneling. But anyway, yep, so there's that. We go one more step. So you get the idea. Basically, every step of the way, you're going to record the width and how many bound states are in there. So like right now, the width is 1.2 nanometers. We got 1, 2, 3, 4, 5 bound states. So that's how you do 1.2 part A. And now you have to interpret that. So they say that the hint is do a linear fit here for the number of states versus versus the width of the box. So do a linear fit, that's your hint. And then use that second plot and try and interpret it. And as I've talked about in class before, interpreting your results isn't telling me how you got them. Right? Don't say, well, first I moved the slider and then I recorded a number. No. I want you to take what you understand about quantum mechanics, go back to your textbook and read it, think about it, etc., and try to explain why you're seeing the behavior you're seeing. So I'm guessing the behavior is that it's linear, right? The number of states is roughly linear as a function of the width of the box. And of course, go back to the equations for the particle in a box, right? So here they are in our textbook. It's page 325 in your textbook. We've got some equations there. Go back to that. We want a quantitative explanation here. Maybe some qualitative as well, but if you can tie in the equations, then great. So you need to explain that. So I'll leave that up to you to figure out. And I also said to look at 1.2 part B. So that's here. Write down all energies of the eigenstates in the potential well for D equals 2 nanometers and plot them as a function of the quantum number n. So the lowest state is n equals 1. Okay, right. So basically, yeah, as we've shown with these quantum states, we have these integer values, right? That for quantum number 1, quantum number 2, 3, etc. Right? You've seen it in this equation right here. The energy states, this n right here, the n has to be an integer, right? So that's what we're talking about, the quantum number here. And of course, you may remember from other chemistry classes you have where you learn about the quantum numbers of electrons when you're looking at electron structure within an atom. So yeah, it's the same thing. We're talking about quantum numbers here. Let's see. So okay, so every step of the way, write down all the energies of the eigenstates. Okay, the eigenstates are these states here. That's what these things are. Are these basically these single wave functions. So because we can combine these things. If we combine them, it's called the superposition state. But we're just talking about individual states that correspond to a single energy value. So this is energy 5, and the wave, the probability density function looks like this. It's the fifth excited. It's the fifth energy level. So that's the fourth excited state. If the ground state, we call this ground. First excited state, second excited state, third excited state, fourth excited state, right? But the quantum number here is 5, because that's it's E5. Here's the fifth one. So it has that energy. It has this wave. It has this wave function, right? So this thing, there we go. It has this wave function, right? It has this probability density function, and it has this energy value, right? They all go together. But my point is that it's the single quantum number 5, right? We're looking at 5 if we plug 5 in, right? So if we're looking at the book, it's 5 here, right? Or it's 5 here. Here's the wave function, right? We have 5 for the n there. If we're looking at the energy, there's a 5 here, right? So if I'm only looking at one of those single states, then that's what I'm talking about by an eigenstate. So when they say eigenstate, that's what they're talking about. Okay, so write down all the energies of the eigenstates for D equals 2 nanometers. Okay, so D is 2 nanometers. So I assume they're talking D. Did they define D? I'm worried that D might be the depth. Yeah, exactly. It has to be D, right? Because we only have one spatial dimension, right? So for a split second there, one thing a mistake you can make with the particle in the box is you look at this thing as a height, just because we're plotting it as a height, but this is an energy. There's only one spatial dimension here, right? This is a one-dimensional particle in a box. So D is a distance. It has to be this dimension right here, right? So for a split second there, I got confused, right? I made a silly mistake and thought, wait, am I changing this value or that value? But it's D, it has to be this one. It's a distance, and they gave me the units, right? Always let the unit be your guide, right? this is nanometers, 2 nanometers. So they must be talking about making this thing 2 nanometers. Okay, so I've made the width 2 nanometers. And what do we want to do? Write down all the energies. Okay, well, we can get the energies, but just by clicking on these things, right? Or hovering over even, right? So the first one, minus 4.92, minus 4.68, minus 4.29, etc., right? Okay, well, that's easy enough to do. So you'll have to record all those things for this D equals 2 nanometers and plot that. And then what they want you to do is compare that with a particle in a box with infinitely high walls. Okay, so remember this box, this particle in a box, this has a depth of 5 electron volts. Right, so sort of the barrier that the particle has to escape is a barrier that has like an energy of 5 electron volts. But of course, you know, if this was infinite, it would look more like this, right? I can raise this energy or lower it. And we see that as I increase the strength of the box, do you notice how this probability density function, it contracts a bit? If I bring it all the way down, it gets wide. Whoops. If I bring it all the way down, it gets wide, right? Choose the ground state. If I bring it top, it gets wide, it gets thinner, right? So basically, the stronger the box is, the more the particles contained. That's not super surprising, right? Yeah, let's put it back where they told us to put it. 0. Is that 0? Height? Oh, not quite. 5. There we go. We need 5 electron volts. Okay. Anyway, so yeah, you're going to want to plot all those values and compare that to if you do the same thing for the perfect quantum particle in a box. So going back to this one, here's your energy values, right? So if we have quantized energies for a particle in a one-dimensional box, okay, so for this one, they don't specify that it's an infinitely strong box. But I think they defined that earlier in the chat. Yeah, here we go. You see how we're going up to an infinite potential energy here? So here we have infinity signs. Yeah. So, you know, these are solutions for the infinite case here. And the simulator here allows you to kind of play with the strength of the box. So it's actually easiest to assume that the box is infinitely strong. It's harder to do what the simulation's doing for us here. So what you're going to do is you're going to plot those two things and look at the difference. And again, you have to try and explain that, interpret it. All right, so that's part A. I think we've covered part A pretty well. All right, part B. Oh no, sorry, that was part B. Okay, we're done with that one. Okay. Let's see. All right, we are trucking through here. Okay, now all of section 3 I said to do. Okay, let's see what section 3 tells us to do. I think this is a harmonic oscillator, if I remember correctly. Yes, harmonic oscillator. So now we are looking at the harmonic oscillator problems here. I told you to do A, B, and C. Alrighty, so reset all and then select harmonic oscillator. Okay, so this is what we have to do with the simulator. So we go back, let's go reset all, yes, and then where is it? Ah, see how we have a square potential well here? There's a drop-down menu, harmonic oscillator, that's your choice as well. Oh, there we go, cool, hey. So now we've got our harmonic oscillators. This is a little different. Now let's see what they want us to do with this thing. So basically, if you look at the potential energy here, let's just compare the two real quick. So here we have a square well. This is me saying, like, if you imagine that yourself, one way to think about these things is you can think about them a little bit like if you're walking around on a potential energy surface, right? So if some terrible person dropped you in a well and you're climbing out, you're at the bottom of this well and you're walking back and forth trying to find a way out. That's basically like, that's kind of what's going on here. It's just square. You run into a flat wall and basically it goes from 0 resistance to running into a wall. You know, it's fighting you at, you know, however many electron volts this depth is. So that's what a square well is. You know, the particle, it feels nothing and then it hits the wall and it feels everything, right? Or if this was you walking around in here, you'd be walking on a perfectly flat surface and then you'd walk smack into a wall, right? But if we have the harmonic oscillator, this is kind of now if you were walking in this thing and you started walking one direction, you go uphill. And the further you go, the further up, the steeper the hill gets. And there's no end to this, right? It just gets steeper and steeper and steeper. So this is different. So now if you're the particle, you're trapped in a different type of well that has this kind of rounded bottom, and either direction you walk, you're walking uphill, and it gets steeper the further you go away from the equilibrium point, which is the center here. So that's what a harmonic oscillator is. And this is like a ball on a spring, right? If you think about the potential energy of something on a spring, right? If this was the center of a spring here, I had a ball and I pulled it back, the potential energy would go up, right? Because I deformed the spring. Or if I start here and I squish the spring, now I've deformed it the other way, the potential energy again goes up. Whether you stretch or compress a spring, it fights you either way. So a harmonic oscillator, you can think about it like a spring, and if you think about the potential energy function, you can kind of think about it as if you're walking up a hill that gets steeper and steeper the further you go. Okay, so that's what this thing is. But basically, we're saying like, okay, now what if this harmonic oscillator behaves in a quantum mechanical way? So now things are different. Okay, so step 1, or step A, 3A. Click on the double arrow symbol at the left-hand side of the potential curve and drag it left and right. Double arrow at the left-hand side. There it is. Okay, so if I drag this thing back and forth, what's this going to do? Oh, cool. So this thing, this controls basically how steep that hill gets. Or if it's a spring, it controls how stiff that spring gets. If I go like this, that's a really stiff spring. This spring, you see how, like, you know, as I say, it fights you the more you stretch it or compress it away from equilibrium. And the more, the kind of the taller and skinnier I make this thing, the more it fights me. So this is a stiff spring. This is a kind of a loose spring, right? If we're thinking about this thing as a spring that we can stretch and compress. Cool. All right. So that's what we're doing when we move that thing. Let's see here. Explain the behavior of the energy levels. Okay. So I told you what the spring is doing, right? This is our spring coefficient. So if you remember Hooke's law, 1/2 kx squared, this is k. That's what I'm playing with right now. I'm playing with k, the spring coefficient. But they're saying, okay, fine, you know what a spring does. But what are the energy levels doing? That's what the question wants to know. So if we look at these energy levels, first of all, notice the spacing of them. You remember how the spacing of the particle in a box, they were closer together at the bottom and got more and more spread out the higher you went. But look at the quantum harmonic oscillator. These things are evenly spaced. Well, that's interesting. So that's just something to make note of. It'll probably come up later if I'm guessing correctly. But look at the energy levels. The stiffer I make the spring, the less energy levels we have, right? I make this thing as stiff as it gets, you know, and granted, you know, you can make this thing plot higher than 15 electron volts, and you know, they'd keep going up. So it's not like with the particle in the box, how you get to the point where the states are no longer bound. That's not what we're talking about here. It's a little different. But basically, you know, the tighter these things are, the higher you make the spring constant, the stiffer the spring gets. The spacing of the energy is getting larger, right? It's all the same space, right? Like if I look at this one's at 8.13, that's 8.98, it's 9.84, right? So this is, you know, I don't know, roughly 0.1 something different, right? It's the same sort of gap, right? The gap between these things is what, 0.13 or somewhere in that neighborhood, right? But if you look at the difference between all these, it doesn't change. But if, you know, as the spring gets stiffer, right? As I keep increasing the spring coefficient here, this gap, it's consistent between states, but it gets bigger. So that's kind of the thing to note here. And sort of this is sort of, you know, if a really stiff spring, you know, the effect of the quantization is more pronounced than if it's larger, right? So basically, you know, this is all quantum. These states are all discrete, but the step between them gets smaller for the sort of the floppier this thing can be. And, you know, that sort of aligns with the particle in the box too, right? Because basically, if you're at this energy level, you can kind of be anywhere in between here, right? If you want to measure where this thing is, you know, even if we're just thinking of a classical one, you have this much energy. You can be anywhere in between here. So this is almost kind of like making the box bigger, right? Having a looser spring coefficient. whereas this is like making the box smaller with a bigger spring coefficient. So the stiffer spring is like the smaller box, and the looser spring is like the bigger box. One other cool thing to look at here is that, if we click on one of these, I want you to think about this thing. Visualize in your head something bouncing back and forth like a spring, right? And look at the shape of this probability density function. That basically, you see how it's like bigger on the ends and narrower in the middle. And if you imagine something that's bouncing back and forth from left to right, at the ends where it has to turn around, it hangs out there longer, right? If something is bouncing back and forth on a spring, right near the equilibrium point, it's moving the fastest. So it goes flying by that point, and then it kind of hangs out on the ends longer. So look at the shape of this probability density function. It's quantized. Like, you can't find this thing just anywhere, right? There are nodes to the wave function that produce nodes in probability density, where like exactly at this point, you will never see the particle there, ever, right? But you're more likely to see it towards the ends than you are in the middle. So although, it does have this quantum effect, it does still kind of match your intuition a little bit. And if you think about higher energy states, if I go all the way up to this one, look at how far out these things go. So again, if you think of something that's bouncing back and forth on the spring at a higher energy, okay, I've pulled it back further and it's bouncing back and forth from left to right, like it's covering more distance as it stretches back and forth, right? Or if I go to a really low one, here's one where, it's still more likely to be found in the ends, but it's just kind of bouncing back and forth a little more calmly, right? But, you see how the higher the energy level, the further it goes and the more pronounced this effect, where you're more likely to see it on the very extremes. So I think that's really cool. So I just kind of wanted to point that out. It's not part of the questions, but this should give you some intuition that, okay, I am looking at something that, maybe you haven't thought about a quantum harmonic oscillator, but, a harmonic oscillator is not such a crazy thing, because, we've all seen a spring bouncing around in some capacity, right? So yeah, just want to make a quick point of that. All right, so if we look at 3b now, so we're done with 3a, let's look at 3b. On the right-hand side of the sim, there's a sliding bar where you can vary the mass of the particle. Describe your observations. Why does the level spacing not change in this sim? Okay, so here's our levels. Pay attention to the spacing. Here's the particle mass. So you watch the spacing, I'll move the mass. It doesn't do anything, right? The spacing of all of our excited states, they all stay the same. Now, if you watch the probability density function down here, that does change. So it's not like changing the particle mass does nothing, but the value of the energy does not change. So why is that? Maybe this is a little unexpected. We have to think about this here. So, well, let's look at the equations for the quantum harmonic oscillator. I like, Georgia State has this thing called Hyperphysics. Really cool website. I like it. They've got a lot of good stuff on here. So we're going to look at their description of the quantum harmonic oscillator, because I like how they've done it here. And here they show the energy level. This E sub n is n plus 1/2 times h bar omega. And omega here is 2 pi times the frequency. Okay, so the frequency of the harmonic oscillator. And how do we define that? Well, that's down here too. Frequency is the square root of k over m, the reduced mass. And if you assume that your harmonic oscillator is just a single mass, okay, so here's a spring here. If you imagine that we only care about this part right here, and this end of the spring is anchored to something, this mass is just your mass, right? But they even include the equation for the reduced mass as well, which is great. Because if you want to, a common thing that you want to do with a quantum harmonic oscillator is think of something like maybe, an O2 molecule, right? Oxygen, O2. You might want to do that with this, the reduced mass here, and then your K value would be, basically if you were to fit a harmonic function to the energies that the quantum mechanical energies that you can measure as you stretch oxygen bond, you could fit a value of that approximately gets the right shape of the harmonic well there. But anyway, so this is what everything is here. And so we're finding that as we slide the mass, it's affecting our wave function, but not the energy levels. So here's the function for their energy levels. And we got n. Okay, mass doesn't show up in that. That's a half. There's no mass there. This is just Planck's constant, right? Divided by 2 pi. H bar is what we call it. That's a constant. So if we look at omega here, let's see, omega we have here. We do have a reduced mass here. Is something that makes up omega here. But okay, so what does this tell us about the simulation here then? So basically, like, they made a choice with the simulation that you can change the mass around, and you can and it will change this omega. Let's see. Yeah, we can change the mass around, but the energy levels aren't changing. So if I change the mass, the energy levels aren't changing. This is the equation for the energy levels. So then what must be happening to K if you change M? Right? Because if you changed omega in this expression, it would change the energy, right? If you changed omega. So this is kind of like, what choice did they make in the simulation so that when you slide the M around, it does not change the energy level, right? So look at this, how we've defined omega, how it goes into the energy thing, and that's going to be how you answer this question, right? So let me zoom in on that again. So this is on hyperphysics. Yeah, this is Georgia State, so gsu.edu. That's where this is from. So, and yeah, actually, yeah, maybe I'll include a link to this in the description too. Okay, so that is that's how we approach this problem. So I want you to sort of think about what's going on with that. I basically gave you all the right places to look of what's happening here with 3b. So basically, if these energies aren't changing when I slide the mass around, what must be going on with how they've set up the simulation to relate K and M? So think about that. Okay, now we're going to say push the reset all button on the right side. Okay, so they want us to reset the simulation again. Reset all. Yes, reset. Okay, we did the reset all. And again, we are going to choose the harmonic oscillator. There it is. Back to harmonic oscillator. Okay, try to remember the curvature of the potential and slide the mass all the way to the left. Okay. Okay, yeah. So as I said, the curvature of this spring, this is kind of like, if the spring is getting looser or stiffer, that's what we're seeing here. So if we slide the mass all the way to the left, this is kind of equivalent to like a looser spring here. Okay, so let's go back to the question, all the way to the left, then use the double, okay, then after we do that, use the double arrow to recreate the potential curve that we saw before. Okay, this is interesting. Okay, right. Okay, so maybe how you want to do this, you can use screenshots. That's probably a good way to do it. So first, let me reset it again because I can't remember where it was. Reset all, yes, and go back to harmonic. Okay. So maybe take a screenshot of it as it looks now, right? And then they say slide the mass all the way left. Then what you're going to do is you're going to kind of eyeball where this thing was before and try and match it. But the way you're going to try and match it is use the double arrow symbol to get it to look like it did before. Okay, so wait, which symbol? Probably not this one. Yeah, it couldn't be that one. It must be this one. That wants to slide. There we go. Yeah. So slide it kind of the way it was before. Okay, right. So again, the default setting was here. Screenshot that so that you can get a good idea of the shape of the harmonic potential here, this parabola. So get a good look at that. And then it said slide the mass all the way left, and then use this slider to kind of make it look like the way it did before, right? And you'll note that the energy levels are different. These energy levels do not look the way they did before, right? The spacing got a little bit bigger than it did previously. So let's see. So how did the energy levels change? Well, I just told you that the gap got larger between between each energetic state. And explain the behavior of the energy levels when you do this in your own words and with an equation. Okay, cool. I like that. It's good wording. So I want you to use your words and your equation. I like that. Okay, so basically, go back to the hyperphysics page, look at these equations, and try and explain what's going on with this. why is it that the energy gap, to get basically the same stiffness of the spring, right? We went with a low, so we had, the mass was, I don't know, somewhere around here, right? The mass was higher and the potential was something like that, right? And then we said, okay, now I want to make the mass really small and then bring the potential here. So, back to where it was roughly, it was about there. And we say, okay, now this gap here is different, right? The gap, is different. So how do you explain that? And again, like the shape of the harmonic potential here, that's kind of how stiff the spring is. The steeper that thing is, the stiffer the spring, right? But then, it's okay. Yeah, notice the units of this thing. So this is omega. So when I hover over this thing, this is omega, and it's inverse femtoseconds. So that's a frequency, right? 1 over time is a frequency. So basically, right now I'm adjusting omega, and this is how I adjust mass. And here's omega, and there's mass, right? So they're all, there's everything you need basically to explain this. So you're gonna have to try and figure out how to explain that. All right, let's see. Is that all of it? I think that's everything I asked you to do. Let me double check. All of section 3. That was section 3, right? Yeah. Okay. So that's good. So that's what you were expected to do for this assignment. So I hope this was helpful. At least now you kind of feel like at least you had somebody kind of helping you through it every step of the way. All right. Good luck, and I look forward to seeing how you do it on this. All right. Take care, everybody.